Objectives for this video is that you'll be able to identify the relative electronegativity, atomic radius, and ionization energy of an element based on its location on the periodic table. Chemical periodicity. There are several repeating periodic trends on the periodic table. That's why it's called the periodic table. Here are some things you already know. It's set up in order of increasing atomic number. Elements in the same group or family are similar in properties to each other. Elements in the same family have the same number of valence electrons, and then elements in the same period are different as you go across the periodic table. Atomic radius is the distance from the center of the nucleus to the outermost energy level of the atom, so it's basically the size of the atom. If you'll look here, from the nucleus to the outermost energy level is going to be the atomic radius, basically. So on the periodic table, this is where the smallest element is found, and this corner over here is where the largest element is found. Francium is the largest of all the elements, has the greatest atomic radius, and you can think of it as fat francium. Francium is the largest atom. Okay, so let's explain why this happens. As you go from left to right across a period, the atomic radius gets smaller and smaller because there are more protons in the nucleus, more protons within the same energy level, which means there's a stronger pull between the nucleus and the outer electrons. So here I have 3 protons, 3 electrons, and so those are attracted to each other and pulling inward, but as I go across the periodic table and I add even more protons, like if I get up to fluorine that has 9 protons and 9 electrons, and now those 9 are just pulling at each other even stronger, which is causing the atom to shrink inward towards the center. As we go down the group, it's a little more obvious why the trend is that the radius increases or gets larger, because as we go down the group, we add an energy level for each row. The atomic radius gets larger. Electrons in the inner energy levels shield the electrons in the outer energy level, and this is called the shielding effect. So here's lithium, which is on row 2, which is going to have 2 energy levels. Energy level 1, energy level 2. Then you look at cesium, which is on row 6, and it's got 6 energy levels. 1, 2, 3, 4, 5, 6. And so clearly it's a much larger atom because it has more energy levels. And the more energy levels you have, the more shielding is occurring for electrons at the outer energy level. And it's known as the shielding effect. Let's dive into the shielding effect a little bit more, as well as what's known as effective nuclear charge. So, as you go down any family on the periodic table, the number of shells increases, number of energy levels increases, 2 energy levels, 3 energy levels, 4 energy levels. And so what that means is the nucleus is getting more and more shielded between it and its valence electrons, or it and other atoms. And so this has 2 shields, this has 3 shields, this has 4 shields, okay? Shielding the nucleus from the attraction with its valence, or shielding the nucleus from its attraction to other elements' valences. Then we look across a period, and the shielding is the same across a period. We have 2 energy levels across every element in row 2 on the periodic table. So what's important and what's changing horizontally is the number of protons there are. 3 protons, 4 protons, 5, 6, 7, 8, 9. And so notice every time we add a proton, our atom is shrinking. It's getting a little bit smaller, and that's because the protons and the electrons on this shell are just pulling even more strongly toward each other, causing the atom to collapse towards the center and get smaller and smaller. Let's list the following elements from smallest to largest, and then here are our 4 elements, and they are on the periodic table down below. So we're going to go from the smallest to the largest. We said at the top right here is where the smallest element is, and of course francium at the bottom left corner is the largest element. This means the smallest element is going to be fluorine, and then the next element bigger than that is going to be the zinc. So we have fluorine followed by zinc. Then the next element that's even larger is molybdenum, which is Mo, and then finally the largest element is going to be francium. And so this is in order from smallest to largest, or in increasing size. Ionic radius is going to be the size of ions, and we use electron configurations and the number of protons to determine the ionic radius. So you first compare the ionic radius to its original atomic size before it gains or loses electrons. And cations are going to get smaller in size because the atom loses an energy level. Anions are going to get larger because the atom gains an electron, which takes up more space. Also, it increases the electron-electron repulsions, meaning the electrons have to spread apart in order to accommodate more electrons. So if we look at the chart here, it's showing you the neutral atomic radius for lithium is 134, and then when it becomes a +1, which is a cation, then it's got an atomic radius of 90. So the radius got smaller. Over here, when we gain electrons, so this is neutral oxygen, has a radius of 73, but when oxygen gains 2 electrons and becomes an anion with a -2 charge, its radius becomes 126. It got larger, and it's because as you add electrons, they have to spread out and make room for the new electrons. Create illustrations of the difference between a neutral magnesium atom and a magnesium cation with a +2 charge. So over here we have 12 protons, 12 electrons. It's neutral. But if we lose 2 electrons, go from 12 to 10, that means I'm going to lose 1, 2, and now notice this energy level is empty, so we lose that energy level, and so now we're down to just 2 energy levels instead of 3, and so of course this cation is smaller than its neutral counterpart. If we illustrate the chlorine neutral atom versus its -1 anion, here chlorine has 17 protons and electrons. So if we add an electron to the chlorine, there's my extra added electron that I'm going to bring in. That means that this whole atom, all the electrons, have to spread out a bit to accommodate that new electron. They are repelling each other, and so it causes the cloud to spread. And so an anion has a larger radius than its neutral counterpart. Ionization energy is the energy needed to remove an electron. As you go down a group, the outer electrons are farther away from the nucleus. Because they're further away from the positive center, they're not held as tightly to the atom, and this makes it easier to remove an electron as you go. So if you look at lithium compared to cesium, here's the valence. Lithium has 1 valence, cesium has 1 valence. Lithium's 1 valence is only 2 levels from the nucleus, and the nucleus is what's holding it close to the atom. And so because this valence is so close to the nucleus, it's got a stronger pull of attraction, therefore it's going to be more difficult to take this electron from the atom or remove the electron from the atom, and so it has a greater ionization energy. If you look at the valence on cesium, it has 5 shields between it and the nucleus, and so it's very far away from the nucleus, so this pull is very weak, and therefore it's going to take less energy. It'll be easier to remove this electron. And so ionization energy gets less and less as you go down a family. So note, the further the valence electron is from the nucleus, the less energy that is required to remove it. The lithium valence would require 526 kilojoules of energy. Sodium has 1 more shield, and so it requires even less energy, 502 kilojoules per mole. And then potassium has another shield, another energy level, so that valence electron requires even less energy to remove, 425 kilojoules per mole. Once an electron is removed from an atom, the nucleus holds the other electrons more tightly, and so it requires more and more energy to remove additional electrons. And if you look at this graph, I would remove 1 electron and it requires this much energy, and then to remove a second electron it requires a little more energy, to remove a third electron even more energy, to remove a 4th electron even more energy, and notice that the requirement of energy increases for each electron you try to take from an atom. And then once you get to the point where it has a full valence, like here, then it requires a tremendous amount of energy to take that electron because it wants that full energy level. Electronegativity is the tendency for an atom to attract electrons when it is chemically combined with another atom. The noble gases are omitted from this trend because they don't tend to form compounds. They already have that complete octet that all atoms want. So the shared electrons will be closer to the more electronegative atom, which is similar to a tug-of-war. So for example, fluorine has an electronegativity of 4.0, francium has an electronegativity of 0.7, so fluorine has the strongest ability to pull electrons to itself, attract electrons to itself. And so if these were bonded with each other, then all the electrons would be pulled toward the fluorine and pulled away from the francium. So fluorine is the most electronegative element of any element, and francium has the least electronegativity of any element. Note that noble gases have a 0 electronegativity value. And so electronegativity increases as you go to the right and up the family, and noble gases are blacked out because they don't have an electronegativity at all. So as you go down a group, electronegativity decreases because the outer energy level becomes farther away from the nucleus and is shielded by the inner electrons, by the inner energy level electrons. The nucleus has less of a pull of attraction for the shared electrons. As you go across a period from left to right, electronegativity increases, and it increases because electrons are held tighter and are pulled closer to the nucleus, and there's a greater attraction toward the center. So let's kind of summarize horizontal trends. As you go from left to right, the size gets smaller, and it gets smaller because more protons sucking everything in. The ionization energy is going to increase, and the electronegativity is going to increase. If I go down a group, the size of the atom gets larger because of increased shielding, or more energy levels are added, so size increases. Then the ionization energy to take electrons is going to be less at the bottom of this family, so that trend will decrease. And electronegativity is weaker at the bottom of the family, so that trend will also decrease as I go down the family. So francium is the largest atom with the lowest IE, ionization energy, the lowest EN, electronegativity. And note this figure is not drawn to scale. And fluorine has the highest electronegativity. So here's a quick summary of each of the trends. The radius is the smallest at the top right, gets the largest at the bottom left. The ionization energy is the lowest for francium, the highest for helium, and then electronegativity, noble gases don't have it. It's the lowest for francium, and it's the highest for fluorine. So now we're going to do some more work in class together on these trends.